Right. So I considered this material time derivative by using the temperature as the physical property of interest. But later on, I started to then basically consider, okay, what if it's something else? What if in particular it's the velocity? तो उस पे I'll come to that. So सबसे पहले तो इसी वजह से क्योंकि इस chain rule के अंदर velocity आ ही रही थी, so we did discuss what the velocity of the particle is. Of course, वो velocity of a particle होती है हमेशा. It's not really, whenever we're talking about the velocity, we are not talking about मतलब it doesn't make sense to me personally कि how else would we would be referring to the velocity of some particle, right? तो इसकी वजह से
मैं recording start करना.
Yes, thank you. Done. So the velocity, its definition itself is something that is a material derivative. मतलब ये it is the property of a particle. That's why it involves the differentiation with respect to time, keeping capital X fixed, right? Or what are we differentiating? Of course, वो तो particle की current position है, right? Velocity is the rate of change of a particle's position. So that's why it's this material derivative like so. ठीक है जी. So we'll do अभी I think it's maybe best कि we already do an example और इसी से आगे we carry on our discussion. So let's jump right here. So this is our velocity. As we've just discussed, it is a material derivative to begin with. Okay, or I know that last time we had already discussed the acceleration as well, but today we're gonna change it up a little bit ताकि रिपीट भी हो जाए और थोड़ा सा आगे भी चल पड़ें और साथ ही पुराना reinforce भी हो जाए, right? So let's look at an example for the velocity. Okay, so in case you guys don't have pens and papers and calculators with you, you please abhi go get something, because your understanding will only be complete if you solve it yourself and we all sort of discuss it together. Okay, it's not enough to just read what I'm doing, you have to solve it yourself. Okay, so I'll wait for a couple of minutes for people to bring in pens and papers, और also कि हम सब इसको आप लोग individually खुद पहले पढ़ें and then start having a go at it before I start as well. Okay. So the position at time t of a particle which was initially at this position, जो मतलब this is its reference position, is given by the equations right here. So these are, so to speak, the path lines showing us कि जो particle originally in coordinates पे था वो अब किस current उसकी क्या x1 coordinate क्या है, current उसका x2 coordinate क्या है, current उसका x3 coordinate क्या है. Okay. Now what we're being asked to do is to find the velocity at a particular time for a particle that was at this reference position. ठीक है, चलें पहले A part तो ये हो गया. Okay, velocity find करनी है. ठीक है. तो I think सबसे पहले तो मे बी ये ये एक एनिमेशन रह गई है इसलिए इधर ऐसे रह गया. सबसे पहले तो probably what would be best for us is कि we write down the expression of velocity, right? So in terms of the velocity मैं ऐसा करती हूँ कि I have my x1 coordinate, I have my x2 coordinate and I have my x3 coordinate. So of course I think चलें ये भी expand करके देख लेते हैं. Velocity in index notation was vi is equals to d xi dt, right? सबको याद है ये कैपिटल D का क्या मतलब था. The capital D meant del of xi with respect to del t keeping capital X fixed. ऐसा ही है. So now let's see. ये I है, मतलब ये कि अगर I के अंदर मैं V1 सब्स्टिट्यूट करूं, then I know कि इधर भी I ही सब्स्टिट्यूट करना है. That means कि V1 is actually the partial differential of x1 with respect to time keeping all, इधर मैंने अभी इसलिए नहीं लिखा था, I'm going to come to this, keeping just x fixed. मतलब इसको मैं या तो डबल करके लिखूं इस तरह, या फिर आई राइट डाउन कि x j को फिक्स्ड, ऑल x1 x2 x3 को फिक्स्ड रख के within the expression. Okay, so let's do the differentiation of this. V1 turns out to be what? इसकी differentiation, right? इस पूरी expression की. और x1 x2 x3 will be kept fixed, which means कि they are treated as constants. So the only the variable that we're differentiating is with respect to time. It's just this one, t. So I get v1 is equals to what? K times x1 plus x2. That's pretty straightforward. What about v2? इधर ही कहीं लिख देती हूँ मैं. v2 क्या होगा? v2 is when I is equals to 2. So that is the partial differential of x2 with respect to time, keeping capital X fixed. So that is what? It's the derivative of this with respect to time only. So t is just with the power of 1. So its differential would turn into just what? K into, again, x1 plus x2. Interesting. So v1 is just equal to v2 basically. And finally, let me also just pop down what v3 is. And I think that is intuitively clear to us that third position जो है, the third component of position is not changing. वो reference position पे ही रहता है. So this v3, which is del x3 with respect to time, as I can see, there is no time dependence, is just 0. Right? So it's turning out that v1 is equals to v2 and they're equal to this particular thing. So अब देखते हैं, we're being asked to find the velocity at time t is equals to 2 for the particle that was at this position at the reference time. मतलब ये कि t is equals to 2 है और particle कौन सा है? x कौन सा है? xi उसका क्या है? 1, 1, 0. That is, its x1 is 1, its x2 is 1, and x3 is 0. So all I need to do to find the velocity of that particle is to substitute in these values for x's and the value for time. क्योंकि velocity तो मुझे given ही मेरी क्या कहते हैं material coordinates में है. It is given in terms of the particle's initial position. So that makes my life much simpler. And I just need to substitute it in. So I get v1 is equals to time तो है ही नहीं. So it's just k times 1 plus 1, right? x1 भी 1 है, x2 भी 1 है. So it's just equal to 2k. Or of course v2 is also equal to v1, so that's also just equal to 2k. Or v3 I found is 0. So that means that if I want to, I can write, या तो आप उसके components सिर्फ we can just leave them as they are, v1, v2, v3. या फिर it's always nicer to represent these things, the tensor as a whole, ताकि we can just get a picture as it is. So v is what? It's either you can represent it as a column vector, this is 2k, 2k, 0, or it's the same thing as representing it as a row vector, उसमें भी कोई issue नहीं है. they're the same thing, right? They're just vectors. We have no, these are not matrices, right? हम vectors की बात कर रहे हैं, just 3 components. या फिर we can represent them in some other tensor type notation, which is 2k in the, let's say, basis vectors, I'll call it E1 की direction में, plus 2k in the E2 की direction में, plus 0 in the E3 direction. फर्दर इसी को लिखने का एक और तरीका भी है 2ki plus 2kj. Right, so it's pretty straightforward for now. Question? No. Okay, so ये तो आसान हो गया A part, because हम velocity find कर रहे थे for a reference particle. मतलब velocity was known in terms of capital Xi and time. ये कर देते हैं ताकि सारे आ जाएं उसके अंदर, और हमें बस फिर सब्स्टिट्यूट करना था. अब लेकिन आते हैं पार्ट बी के ऊपर, which is again, sorry for this. Actually, let me just move through that's the solution already in the slides as well. Let me move to part B now. Okay. Now, what we want to do in B is, we want to find the velocity at the same time, but for the particle that is at this position at this time. मतलब ये कि वो particle जो final position जिसकी is 1, 1, 0 at t is equals to 2. Okay, so now what's the issue for us? The issue is कि velocity हमें पता थी in terms of capital X's. V1, and this was also equal to V2, and V3 was 0. ठीक है जी. So अब मेरे पास तो लेकिन small x आ गया है. So what do I do to find the velocity when I have this in terms of the small x? What do you guys suggest? Can I just substitute this directly in here? Can I just point out one thing, that I am making a differentiation between small x and I am making a distinction between small x and capital X. I write my small x as an italic, whereas I write my capital X as a cross. Okay, so please tell me, ये small x है और ये तो capital X के terms में है. What do I do?
Chain rule.
Okay. Chain rule कैसे लगेगा?
मैम simultaneous solve करके x1 और x2 की वैल्यू निकाल लें, capital X.
I feel this might be easier, yes, which is जो अभी your colleague has suggested, कि अगर हमें small x की position पता है और हमें पता है कि कैसे particles move कर रहे हैं space में, मतलब कि वो कहाँ जा रहे हैं at किस time. So why don't we just find कि जब time t is equals to 2 है, तो इस current position के ऊपर कौन सा particle है. मतलब ये कि इसको substitute कर लें into these expressions right here. Now what does that tell me? That tells me, for example, कि x1 is 1 at t is equals to 2, तो 1 is equals to कौन सा particle है वो, जिसकी क्या है x1 plus x2, जिसका time 2 है. Similarly, x2 कहाँ है? x2 is 1. So that's also 1 is equals to this time x2 plus k into x1 plus x2 multiplied by 2. And if I just solve these simultaneously, I can find what is the original particle that is going through this position at time t is equals to 2.
Ma'am,
Ji.
we do have three variables in the equation. There's x1, k, and x2, and we have two equations to solve them with.
K is k is just some sort of a constant. One thing, it's just
Okay.
representing. Essentially, think about it this way. We are talking about the position of a particle, right? So it is implying कि कौन सा particle किस time पे कहाँ पहुँच रहा है. That is, the only variables in these sort of conversations are कि which was the particle, that is, original reference position क्या है और अब क्या time हो रहा है. So these K's sort of things are just trying to make the equations of motion general. मतलब ये कि वो बस कांस्टेंट को नंबर की बजाय एक कांस्टेंट इस तरह के sort of लेटर से रिप्रेजेंट करने का सिर्फ ये मकसद है ताकि वो आप उसके अंदर ढेर सारे फ़र्क पाथ लाइंस को इनकॉर्पोरेट कर लें. समझ रहे हैं?
Okay.
If k had been a variable, that is, if k had also been a function of the position and time, then this doesn't make any sense. फिर तो आपको k को भी x और t के terms में ही लिखना चाहिए था ना, right? ताकि फिर पूरी
Yes, ma'am.
expression होती in terms of the capital X's and T's. So these sort of terms which are floating like so, like K or A or B or etc. etc. So small alphabets, मतलब lowercase के alphabets, they generally just represent sort of क्या कहते हैं scalar constants.
Okay.
You're right that probably it's whenever, for example, you're writing your own papers or in your thesis or any work that you guys produce, these things should be already clearly defined. Okay, where k is just the constant. Okay. Take it. Right. So okay. So k is a constant, which is why the only variables we have here is small x's and capital X's and time, of course. So for the particular current position at this time, we can substitute in those values to find कि उसके ऊपर कौन सा particle है, मतलब capital X क्या है उसके through जो उस वक़्त गुजर रहा है. So when we do that, I hope आप लोगों ने इतनी देर में भी किसी ने कर लिया तो मुझे भी बता दे कि capital X1 क्या आता है. And otherwise I'll have to solve. ये थोड़ा लंबा हो जाएगा solve करना.
मैम कैपिटल 1 minus 2 के
Sorry, please फिर से repeat कीजिएगा.
x1 है मैम 1 minus 2k x2
Okay, nice. Okay.
over
X
1 over 1 plus 2k. Over 1 plus 2k.
लेकिन ये तो x2 के टर्म्स में है अभी.
Yes मैम.
इसको मजीद
मैम सिमिलर आ जाएगा उस साइड पे x1 की टर्म्स में.
I'm not so sure about this because दो equations हैं, दो variables हैं. हमारे पास तो values आ जानी चाहिए सिर्फ k के terms में.
Yes मैम सॉल्व हो सकता है इस तरह.
Yes. So इसको further we can solve this, right? So you mean कि अच्छा आपने पहली equation से ये निकाला है. Now we're gonna have to substitute this in here to find कि x2 just in terms of k क्या है, right?
Yes मैम.
हाँ जी, तो वो करना है ना हमें, बताएं जी. Thank you, Rabia. So once अभी कौन बोल रहे थे, sorry, once your colleague ने जो इस वाली को rearrange किया है, which is x1 is equals to 1 minus 2k x2 divided by 1 plus 2k, बिल्कुल ठीक. I can substitute this into b, ठीक है जी, इसके अंदर ये x1 की value डाल के and then rearrange it to find what x2 is, and it turns out according to Rabia that x2 is 1 divided by 1 plus 4k. Okay. अब आई नो कि मैं थोड़ी डंडी मार रही हूँ, मैंने सॉल्व नहीं किया, इसलिए कि आई एम होपिंग कि आप लोग साइमल्टेनियस इक्वेशन सॉल्व कर लेंगे. और आपको पता ही है मेरी स्पीड पता नहीं कितनी स्लो है, तो मैं करना शुरू करूँगी तो मुझे थोड़ी ज़्यादा देर लग जाएगी. That's why. But essentially, it's just the standard case of solving simultaneous equations. They look a little bit more complicated, which is why once you've got this expression by rearranging A, you got to substitute it into B and then do some arithmetic manipulation. Could anyone else as well please confirm what Rabia is getting? Meanwhile, I'll carry on. So Rabia, if we get this for x2, what does this give us for x1? Thank you, Usman. So इसकी वजह से x1 would be which is
Ma'am,
what?
x1 will be the same.
You're right. So 1 plus 2k and then 1 over 1 plus 4k. Yes, exactly. I'm getting the same thing. Was there a shortcut that I missed, or did you actually have to do the same thing and solve it for x1?
Yes, ma'am, we had to solve it.
Yep, okay. So just was wondering कि maybe यहाँ से हमें कहीं से obvious हो जाता कि x1 and x2 are equal, but I don't think that's obvious to us. Okay, anyway, so yes, so once Rabia had given me x2, फिर I had substituted it in here to find what x1 was. Perfect. So now basically, now we've got all the information we need because हमारी velocity is in terms of the capital X's, and I can substitute in कि मेरा v1, which was also equal to v2, turns out to be what? It's x1 plus x2. So it's 2k divided by 1 plus 4k, and v3 is 0. So that's what our velocity comes out to be. Now this is interesting because let's try to draw this out. Oops, sorry. Let's try to draw this out. So for A, we're getting a velocity of 2k, 2k, 0. And in B, we're getting a velocity of 2k divided by 1 plus 4k, I believe. Maybe I've made some mistake here, but the point is that they're just completely different. Even though if you think about it, we were talking about actually two completely different things when we know what we're talking about. So in A, we are saying that we are looking at in space this is also the same as capital X1s. Okay, in space, reference position अगर ये थी और इसके 110 मतलब let's this point reference configuration में this one. So that's what we were talking about in A. Okay, ये reference particle जब t is equals to 2 पे उसकी क्या velocity होती है. तो वी डोंट नो कि वो एट टी इज इक्वल्स टू 2 एक्चुअली कहाँ जा चुका था, लेकिन रेफरेंस में उसकी यही पोजीशन थी और हमारी वेलोसिटीज़ जो थी वो हम डिफाइन ही इस मटेरियल कोऑर्डिनेट्स में कर रहे थे. वेयरएज इन बी वी आर लुकिंग एट द वेलोसिटी ऑफ द पार्टिकल दैट इज एट दिस पोजीशन. which means कि when at t is equals to 2, this entire body had already moved somewhere else. तब भी हम इसी पोजीशन को देखते रहे स्पेस में, but now if you notice there's some other particle of the body which is going through that point. So in part B, first we are just looking at that point in space. We had to find कि इसके through कौन सा particle जा रहा था. And then we were able to find कि okay, ये जो particle इस position के through गुजर रहा है, उसकी ये velocity है. Right? So be careful about this, that essentially about what this capital X is and what the small x is, and the velocity however is always representing the velocity of a particle, right? So अगर वो reference configuration की बात करें तो हमारे पास वो वैसी की वैसी है, whereas अगर किसी position के ऊपर हम velocity की बात करें, then we're talking about the velocity of the particle that's going through that spatial position. Okay, so not overly complicated, but still something to be a bit careful about, right? So I hope that clarifies a little bit what we were saying, the velocity is for a particle. Acha, either I want to discuss one more thing. Let me erase something. Which is now let's lead up to discussing how can we represent velocity in the two descriptions of position. So one was the case we had noticed how v1 and v2 here was just equal to what? K times x1 plus x2. ठीक है जी. So this is the velocity in terms of capital Xi and time, even though time feature ही नहीं कर रहा है. So it's just what would be the word? The acceleration of the particles is 0, but it is in terms of capital X's. But it was also possible for us, जिस तरह अभी हमने how we had used these equations to rearrange them such that हम x1 को find कर लेते as, और xi's सारे x1 x2 उसको find कर लेते in terms of the small x's, that is इनको simultaneously solve करके rearrange कर लेते ताकि ये small x1 के बजाय मेरे पास capital x1 आ जाता in terms of small x1, small x2 and time, और capital x2 भी उसी तरह आ जाता in terms of the small x2, small x1, small x2 and time, and k भी feature करता. Then what I can do is कि इसी velocity की equation में I could have substituted in x1, capital X1 and capital X2, right? Or when I do that, then I get the same velocity field, मतलब same कि वो particles की ही velocity है, लेकिन that would have been described in terms of the small xi's. मतलब ये कि फिर I would have been looking at कि अच्छा अब I'm looking at a position in space और जो भी particle उसके through उस time के वक्त at that time is passing through it, उसकी क्या velocity है, right? So my point is it's still the velocity field, it's the same velocity field, उसकी description वही है, it is still always the material derivative of the current position, but it can be described in terms of either capital X, or I'll use a hat to represent it, and it could also be described in terms of the small x's, where here I would have just had directly the velocity of a particle जिसकी original position ये थी, whereas here I would have had the velocity of a particle जो space में इस small xi पे था at whatever time. Does that make sense? Right?
मैम रिपीट कर दें कभी?
हुई अच्छा सबसे पहले तो ये कि ये बात क्लियर है ना कि वेलोसिटी एक पार्टिकल की होती है ऑलवेज. हेलो
यस मैम.
राइट. ये इस कैपिटल डी का मतलब ही ये है कि एक पार्टिकल को फिक्स किया हुआ है हमने. राइट. सो द वेलोसिटी इज ऑलवेज ऑफ अ पार्टिकल. और इसी डिस्क्रिप्शन को यूज़ करके हमारे पास लेट्स से एक सॉर्ट ऑफ किसी बॉडी की डिफॉर्मेशन गिवन है. मतलब ये कि उसकी ओरिजिनल अगर ये कोऑर्डिनेट्स थे तो अब उसकी करंट पोजीशंस ये हो जाती हैं, हमें गिवन है. ठीक है. उसकी मोशन गिवन है, मोशन डिफॉर्मेशन जो भी कह लें आप उसकी, वो हमें गिवन है. तो उसी से इस डिस्क्रिप्शन ऑफ वेलोसिटी को यूज़ करके हमने डिफ्रेंशिएट करके उसकी कोऑर्डिनेट्स निकाल लिए सारी वेलोसिटियों के. राइट. हमने डिफ्रेंशिएट किया था कीपिंग कैपिटल एक्स आई फिक्स. So what we saw is कि when we do that, I get my v1 and v2 which is in terms of these capital X's, है ना. तो ये कैपिटल X की डिस्क्रिप्शन में मेरे पास क्या आ गई? मेरे पास आ गई वेलोसिटी ऑफ अ पार्टिकल जो उसकी ओरिजिनल पोजीशन हमें नोन थी. मैं आपको ये कह रही हूँ कि अभी जब हमने एग्जाम्पल के अंदर ही इसका बी पार्ट किया था तो हमने इसी चीज़ को फ्लिप किया था ना, उसकी सॉर्ट ऑफ स्पेशल पोजीशंस को देखने का. हमने ये फ्लिप किया था कि हमने करंट पोजीशन नोन थी, उससे हमने ओरिजिनल मतलब पार्टिकल का नाम या रेफरेंस पोजीशन फाइंड कर ली थी. Which is to say that I can solve these simultaneous equations to flip and find the inverse of the mapping. That is, I can find कि कौन सा particle है, what is the reference position which will be at a particular position in space at a particular time. That is, I can find this capital X's in terms of the small x's. Right? And once I do this, मतलब मैंने कैपिटल x1 और x2 को इनको साइमल्टेनियसली सॉल्व करके फाइंड कर लिया है, तो फिर मैं उन्हीं को इसके अंदर सब्सटीट्यूट भी तो कर सकती हूँ ताकि वेलोसिटी भी मेरे पास इन स्मॉल एक्सेस की टर्म्स में आ जाए. That is, I can describe my velocity in these two different ways. One is in terms of capital X and the other is in terms of the small x. And why that's important is it's coming up now. It's important because velocity se derived, there's another property of interest to us, which is the acceleration. ठीक. Now, acceleration is again, it's a property of a particle. It's not just some random space ki field. It is a property being defined of continuum particles. So again, as with velocity, by definition, acceleration is the material derivative because we follow a particle of the velocity. So acceleration B is this expression. It's the rate of change of velocity of a particle. मतलब ये it is not, sorry इसको ये भी नहीं लिखना चाहिए. It's not del V by del T keeping small x fixed. This is not acceleration. Okay? Acceleration is the rate of change of velocity of a particle. Now that's where the thing comes in which we discussed about temperature as well. That the issue is that this velocity field can be described in two ways. जो अभी हमने discuss किया. One is it can be given in terms of the capital X, right? which we just discussed in this problem. राइट कि ओरिजिनली जब हमने इसको डिफ्रेंशिएट किया था तो हमारे पास वो आया ही कैपिटल एक्सिस के टर्म्स में था. So if that's the case, then that makes our life a little bit easy, because if I'm trying to find the derivative keeping capital X fixed, फिर तो ये velocity की expression भी capital X के terms में, and I can differentiate it in a straightforward manner, no issue. But if the velocity is actually being given in the spatial, मतलब ये it's given in terms of the small x's, जिसको मैं पहले represent करी थी ना, इसको tilde से और इस वाली को with a hat, I think so. तो मैंने flip कर सकती हूँ, maybe I might be mistaken. Then what I'm trying to do is I'm finding the derivative, material derivative of a function which is being given in terms of the small x. So फिर मुझे acceleration के लिए भी chain rule लगाना पड़ता है, और ये बात हमने last time discuss की थी, right? So I was just trying to use the example that we'd just done to explain to you how is it possible कि velocity हमारे पास या तो capital X के terms में हो, या फिर वही velocity field for the same sort of deformation can also be described in terms of the small x's. How is that possible? That's what we were just discussing. Because these are just sort of descriptions of positions, right? So as we've just seen in the examples, it's entirely possible कि वही field, वही velocity को हम इस तरह describe कर लें या इस तरह कर लें. अब बात यह है कि जब small x के terms में हो, फिर हमें वो material derivative, that is capital X, निकालने के लिए हमें chain rule use करना पड़ता है. Okay? Or chain rule comes about as it was before, which is that it involves the partial derivative with respect to time keeping the small x fixed, plus the derivative of the field in space, that is of the field is velocity, so it's the derivative of velocity in space multiplied by the velocity of the particle at that position in space. ठीक है जी. तो ये डायरेक्टली ये आ गया, ये वाला जो है वो वेलोसिटी ये बन गया.
Excuse me?
हाँ जी.
I'm sorry, sir, could you please confirm?
जी जी.
When velocity with respect to our current location and reference location, मतलब capital X और small x, तो velocity तो change होगी ना मैम, velocity तो same नहीं रहेगी ना. तो सिर्फ यही चीज़ confirm करनी है मैम, ये बात.
अगर acceleration नहीं, एक सेकेंड देखिए ना, बात यही है ना कि वो चीज़ें ही दो completely different हैं. मैं आपको जिस तरह पिछली एग्जाम्पल में हम सेम कोऑर्डिनेट्स को देख रहे थे, राइट, हम 1 1 0 को देख रहे थे. सिर्फ इशू ये था कि इन पार्ट ए हम देख रहे थे जो रेफरेंस पोजीशन, रेफरेंस पार्टिकल इस पे था, और इन पार्ट बी हम देख रहे थे कि अब कौन सा पार्टिकल इस करंट पोजीशन पे है, राइट. और वी सॉ कि उन दोनों की वेलोसिटीज डिफरेंट थी. Does that make sense?
Yes, ma'am. Ma'am, सिर्फ ये confirm करना.
Yes, yes. So because basically at the end of it, in part A we were talking about, let's say, particle A, और फिर B में कोई और particle था जो इस position पे था. So we were talking about some other particle B, right?
जी मैम.
ठीक है जी, thank you. Okay. So last time as well, this is how far we had gotten. And today what I want to pick up with further now is to do an example of the acceleration. लेकिन मैंने आपको कहा था कि मैंने quiz लेना था. Yes. So let's अभी let's start to actually get ready for that quiz, because it's the first time we're going to have it, so we might have some logistical issues. So for all of you, we're going to take a little break in class right now. 6:15 pe your quiz is going to start. Let's get back into it. So we are just basically gotten back to the discussion of what the acceleration is. We have done this before, but we're going over it again ताकि ये सारे concepts completely clear हो जाएं. Right. So we saw कि if our velocity is given in the spatial description, that is, it's given in terms of the small x's, it's given in terms of the position, current position in space, then we have to apply the chain rule to find the acceleration of a particle that may be passing through that point in space. Okay, और इस चीज़ के अंदर in the chain rule we have the derivative of the velocity with respect to time, keeping small x fixed. So please notice this is the rate of change of the velocity field, but not of a particle. It's the sort of the rate of change of velocity field described in space. उस चीज़ का है. This is not of a particle क्योंकि small x fixed है. Plus the velocity of a particle being multiplied by the gradient of the velocity field in space. Okay, so this term right here, which in sort of direct notation, if I write it, it's the differentiation of velocity with respect to spatial position. This is the del operator being applied to velocity. Okay, it's del, which is, you know, the partial differential with respect to some spatial position of the velocity. So this thing del xv is of course then referred to as the velocity gradient. Okay, because it's the gradient of the velocity field in space. Or the most important thing from our previous deformation tensor and so on जो हमने sort of static या फिर rates को जब हम नहीं देख रहे थे, तो the important difference is कि previously we'd been looking at gradients with respect to the reference configuration, whereas this velocity gradient is actually a spatial, it's an Eulerian quantity. मतलब ये it's with respect to small x, del by small x, which is the important distinction. Okay, we'll encounter this velocity gradient again in just a second. This is actually a pretty important important term, right? Okay, so let's look at an example to see thoda sa okay, this concept of material and spatial descriptions of velocity. Okay, so we want to find, given this velocity field, we want to find the acceleration field, and then we want to find the path line. That is, we want to find के एक original particle की क्या current position है from this velocity field. So let's think about this. First of all, what I want you guys to notice is कि ये velocity is given in terms of small x's. मतलब ये कि ये हमें नहीं पता कि वो कौन सा particle है जो उस space के position से गुजर रहा है. बस हमें सिर्फ ये पता है कि whatever particle it is, उसकी क्या velocity होगी at a given time. मतलब ये कि let's try to draw this out a little bit. Let's consider again कि दोनों are being defined with respect to the same frame of reference. So let's consider कि मेरी original reference configuration was something like this. Sorry, ये capital X थी. अब क्या हो रहा है कि this body is in motion, and because of that motion, let's say कि वो कहीं move कर रही है. I'm not अभी in particular interested in exactly how it's moving, but it's moving somewhere. So what I'm doing is कि I'm just looking at the velocity at some particular position in space. Let's say कि ये x1, x2, x3 ना मैं देख रही हूँ 5,5,3 के ऊपर, just as an example. Sorry. So let's say कि वो 5,5,3 जो है ना कोई ये है space का position. और इसके ऊपर I'm looking at the velocity. Now what that means is कि if I'm saying कि my small x I'm considering to be 5,5,3, this point in space, then what I'm doing is I'm just looking at this point and considering कि okay और टाइम भी फिक्स कर लेते हैं, और t इज इक्वल्स टू 3 कर लेते हैं, जो भी अपनी मर्जी से मैं ये बना रही हूँ कि t इज इक्वल्स टू 3 पे इस पोजीशन ऑफ स्पेस के थ्रू जो भी पार्टिकल गुजरा था, और वो पार्टिकल क्या है, वो शायद ये वाला पार्टिकल हो, वो गुजरा था एट t इज इक्वल्स टू 3, तो मुझे उसकी वेलोसिटी पता चल जाएगी व्हेन आई सब्स्टिट्यूट दीज थिंग्स इन हियर। वेयर एज अगर मैं t इज इक्वल्स टू 5 के ऊपर सेम पोजीशन इन स्पेस को देख रही हूँ, देन मे बी उस बॉडी का ये वाला पॉइंट गुजर रहा है अब उसके थ्रू, उसी पॉइंट के थ्रू, right? So then when I'm looking at still again the same point in space but at a different time, then I'm finding the velocity of some other particle. Okay, so that's what this means. That's what this spatial description of velocity is telling me, right? Or ab when I want to find the acceleration, of course now is the tricky part, which is that I know that my acceleration is actually, it's the material derivative of velocity, right? Yeah, right. So it is the partial derivative of v with respect to dt, where either my velocity is being given in terms of small x's, but this with respect to capital X being fixed. So now I have my velocity in terms of small x, but my derivation is with respect to keeping capital X fixed, which means that I need to apply my chain rule. Or what was that chain rule? We all now, I hope, recall. Let me change this into index notation to make my life a little bit simpler. Let's first notice that luckily for me, V1 has the same expression with x1, V2 has the same expression with x2, and V3 has the same expression with x3, which is why I can simply write down that Vi, any 1, 2, 3 is actually a function of just k xi 1 plus kt, right? क्योंकि v1 x1 के टर्म्स में v2 x2 के और बाकी सब सेम है, वो जो कांस्टेंट टर्म है, no sorry, not constant term, क्योंकि sorry there's a t here which is the variable, but at least it's allowing me to write down one simple index notation representation for all of the components, ठीक है? So अब आते हैं हम acceleration find करने पे. So acceleration के लिए तो I know what I need to do, right? Chain rule apply करने का expression मेरे पास है, which is that AI is going to be equal to what? It's going to be equal to del Vi with respect to del t, यही tilde वाला, keeping xi fixed, plus मुझे थोड़ा सा भूलना शुरू हो गया इंडेक्स नोटेशन में क्या था एग्जैक्टली, आई थिंक इट वाज Vj multiplied by del Vi with respect to del xj, right? So I neither do I expect you guys to memorize this, nor do I expect myself to have it completely memorized, because the J's can go a little bit awry for me at least. Okay, वो कौन सा index notation थी? What I do expect is you guys to understand the physical significance of this, and then for us to be able to see the expression and know what we're talking about, right? So luckily for me, मेरा वो जो थोड़ा सा तुक्का की यादाश्त चल रही थी वो ठीक ही थी, right? So that's why it's just worked out that I've got the right expression. Okay, so so this is our acceleration of a particle given that we have the velocity in the spatial field. Okay, so now let's find this out. So the first term is just of course del vi with respect to del t. ठीक है, मैं ऐसा करती हूँ, मैं ना क्योंकि मुझे सब कुछ से नज़र आ रहा है कि वी आई अगर ये हैं सो ए वन मतलब नहीं, ए वन विल बी इक्वल टू ए टू इक्वल टू ए थ्री तो नहीं होगा ज़रूरी. ओके, मुझे इसी तरह जनरल में ही रहना पड़ेगा. आई वॉज अबाउट टू सजेस्ट कि व्हाई डोंट आई फाइंड ईच ऑफ द टर्म्स. तो मैं लेट मी ट्राई टू डू दैट फर्स्ट, क्योंकि ये मुझे कॉम्प्लिकेटेड लग रहा है. देयर आर 3 इक्वेशंस इन हियर, राइट. देयर इज़ ए आई जो आई 1 2 3 तक जा रहा है. तो मुझे सिर्फ पहले A1 निकालने दें, फिर A2, फिर A3, and let's see how they compare. So when I'm finding A1, then I've got del of V1 with respect to del T plus J will stay as it is. The J is a dummy. Del of V1 with respect to del of xj. Okay, now let's try to find this. Okay. So del V1 with respect to del T, keeping xi fixed, या x जो भी कहने हैं, सारे x's fixed है ना. So what is that? It's V1 with respect to time, keeping x1 fixed. क्या हुआ? Differentiating with respect to time, keeping this fixed. This is a constant. So what do you? Could someone tell me what it comes out to be? पहली term सिर्फ. Anyone? The differentiation? I wonder how long it's been since you guys differentiated something like this with the denominator में जहाँ पे term हो. Guys.
Ma'am, kxi divided by 1 plus kt whole squared into k.
Very good. But any minuses?
Minus sign.
Exactly. Just that's the only thing that you'd missed. Perfectly right otherwise. So it's just, ये तो constant है सब कुछ. kx1 फिर 1 plus kt. उसकी power was minus 1 here. So it becomes a power of minus 2 now. Multiplied by the derivative of this denominator term, which is going to be मतलब minus 1 से पहले multiply किया and then minus k. Okay, so this was just this part. अब हमें इसके अंदर plus the summation over j with respect to v1 ये करना है, which is, what does this mean? This is a summation term, right? Let's write that down. It's a summation over j. Remember, dummy index है ना? What does the dummy mean? Is the summation over j as j goes from 1 to 3 for vj del v1 del xj. Or in other terms, this term just comes as it is. So this becomes minus k squared x1 divided by 1 plus kt whole squared. Now here, 3 terms add हो रही हैं. What are those 3 terms? Plus v1 del v1 with respect to, sorry ये 1 है, del v1 del x1 plus v2 del v1 with respect to del x2 plus v3 del v1 with respect to del x3, right? j के ऊपर loop था, right? Okay, so what are these terms? v1 with respect to x1. चलें पहले तो ये वाला ये लिख लेते हैं. This is as it is. I'm sorry मैं इसको दोबारा लिखने के बजाय ये कर रही हूँ. So v1, this thing, kx1 divided by 1 plus kt multiplied by del v1 with respect to x1. This thing differentiated with respect to x1. What is that? It's just everything else is a constant. So the constant just appears as it is. right? Plus V2 with respect to V2 multiplied by V1 with respect to x2. Okay, that's interesting. V1 with respect to x2. V1 तो function ही नहीं है x2 का, which means, look carefully, right? V1 is just a function of x1 and time. So there is no x2 in here such that the differentiation of V1 with respect to x2 is 0. And similarly also for V1 with respect to x3. That's also, there is no x3 term in here, so this is also 0. So all that we end up with is these two terms. And what's happening, if you look carefully, this is actually a minus k squared x1 divided by this, and plus k squared x1 divided by the same thing. So these two are, there's a minus and a plus of the same thing, such that the A1 is actually A1 term is actually 0. Do you guys see it? Okay, actually, I didn't mean do you guys see it, like, but I meant like in your, is that clear? Okay, what just happened?
Yes,
Yes,
ma'am.
ma'am.
Right?
Yes, ma'am.
So I admit the fact that this is not, at least I wasn't willing to directly do it in this format, right? I wanted to first, at least, because if we're doing it for the first time and we're not so confident just using or manipulating expressions directly in index notation, then it's worth just opening up the components, right? So that's why I first looked at A1. लेकिन आहिस्ता आहिस्ता आई होप कि अब हमने A1 कर लिया है, तो मे बी इट्स वर्थ कि वी डायरेक्टली सी कि AI ही कर रहे होते तो फिर क्या होता. Okay, so if we try to do that, actually uske, let me, do I have, nope, okay. So let me erase this, and I want to be a little bit quicker now because I hope कि हम लोग will be able to jump through. So Vi we know is kxi 1 plus kt. Now ai I know is going to be del Vi with respect to del t plus Vj del Vi with respect to del xj. Now let's see. Just keeping it in index order. Del Vi with respect to del t. Vi mein there's just the xi, so we get the same expression as before, which is going to be what? Minus, या फिर इधर से देखें ना, xi stays as it is, so it becomes minus k squared xi divided by 1 plus kt whole square. That's my del Vi with respect to del t. This expression derived with respect to t. Plus then what? Vj वो वही होगा जो हमने अभी पहले किया था, which is plus V1 del Vi with respect to del x1 plus V2 del Vi with respect to del x2 plus V3 del Vi with respect to del x3, right? And in all of these expressions, we've got that one right here as it is. Now let's look at this. So V1 with respect to del x1. Okay, so that is something that exists, right? V1 with respect to x1. Oh, itme kya? Sorry, apologies. Vi with respect to x1. I'm thinking.
Ma'am, I think we can only find it when we put the value of I, like either it is dvi or something like that, the dv1, dv2. If the value is there, then we can solve it. Otherwise, I don't think that we can just nullify these by looking at them with a general expression.
Adan, just a second. Let's just let me think about it first. Okay, I'll have to take a look at this part again. If anybody else can we or can we not? Oh, no, we can. So, this is going to be tricky. So, we can if you think very carefully about it, which is, मैं गड़बड़ करने लगी because I haven't, I should have seen this before and articulated this properly beforehand in my head before thinking out loud. But I'm gonna try my best. So, basically, del Vi with respect to x1. Now, this only exists when what? When I is equals to 1, right? So, मतलब ये कि अगर मैं इसको again मुझे फिर से बोलना है, del Vi with respect to del x1 will only exist when I is equals to 1. Whereas here, del Vi with respect to x2 will only exist when I is equals to 2. And similarly, del Vi over del x3 will only exist when I is equals to 3. मतलब ये कि मैं आपको कुछ कहना चाह रही हूँ कि एक और चीज़ थी हमने जो पहले इनकाउंटर की हुई है जिसके अंदर इस किस्म की एक प्रॉपर्टी है, which is कि when I and J are equal to each other, only then it's equal to 1 and otherwise it's 0, right?
मैम ये यहाँ से जो वेलोसिटी के एक्सप्रेशन दिए हुए हैं यहाँ से नहीं देख सकते कि मतलब जो v है x1 के साथ वो पहले वाले में सिर्फ x1 है, दूसरे वाले में सिर्फ x2
काशिफ, इसीलिए मैंने बोला है कि ये जो टर्म है ना ये वाली यहाँ पे, इसका ये एग्जिस्ट ही, मैं इसको देख के कह रही हूँ कि ये एग्जिस्ट ही तब करेगी, इसको या इनको जिसको भी आप कह लें, ये एग्जिस्ट ही तब करेगी जब I इज इक्वल्स टू 1 होगा। समझ रहे हैं? ये देखें, क्योंकि मुझे पता है कि v1 ये है, तो अगर मुझे del Vi विद रिस्पेक्ट टू x1 निकालना है, तो ओनली जब I 1 होगा तो फिर ही del x1 वाला एग्जिस्ट करेगा। del V2 विद रिस्पेक्ट टू del x1 नहीं एग्जिस्ट करता। समझ रहे हैं? और इधर भी वही बात है। सो ये जो मैंने लिखा बोल रही थी ना मैं अभी कि I इज इक्वल्स टू 1 होगा तो फिर ही एग्जिस्ट करेगा, I इज इक्वल्स टू 2 होगा तो फिर ही ये टर्म एग्जिस्ट करेगी एंड सो ऑन। That is only for this particular case जब velocity की ये expression है। I'm not talking about some general problem. I'm talking about this specific case when I have this expression for the velocity. So what does that mean? That means कि I can actually write this down in terms of del ij, क्योंकि उसकी term ही तब exist कर रही है सिर्फ जब ये I भी वो हो J के ही इक्वल हो। ओके, और अब फिर अगला मसला आता है कि उसको लिखना कैसे है, विच इज़ V हाँ, so this is only true when we have I is equals to J. Oof, however, I'm getting a bit stuck. Essentially these three terms या फिर ये summation can be expressed in terms of delta ij. So from what it seems like it to me, the del vi with respect to xj is just अगर हम del vi with respect to del xi ही निकाल लें, only then does it exist. And what does that value come out to be? It is just k 1 plus kt. That's it. Sorry, I'm getting a little stuck and I will end up spending too much time on it. It's difficult for me to think during a lecture. I have to do all the thinking beforehand. So please excuse the fact that I'm going to jump this right now, or I will come back to it in the next class. I haven't thought about it beforehand. But my point was that ye hum, at least it seems to me that we can express this or solve it in terms of index notation using the permutation, using the Ronecker delta symbol. So let me just see the solution, because iske andar it's already being done that way, of course, which is, yes, that's what I was trying to say. Okay, well, vi just comes out to be this, and it's only true when I is equals to j. That's why, hence the delta ij being right there. Chale, anyway, close enough. In any case, I'm not gonna. In any case, when we had looked at each of the components, we had already seen that A1 was turning out to be 0. Wahi lamba wala procedure we could apply, and I will ask you guys to try it out. Components pe jab karenge to A2 will also turn out to be 0, interestingly, and A3 will also turn out to be 0. So either we do each of the components, which is what we had started to do and we made some headway, कि A1 तो हमने निकाल लिया था, या फिर we just work in index notation, and what we will see is that the general AI will turn out to be 0. वो जब अगर index notation में करते तो वो उसी expression से सीधा हमें तीनों पता चल जाते हैं, right? So anyway, what this is implying is that the acceleration of the particles is 0. This is quite interesting. Why? Because ये देखें, हमारी velocity field जो spatial positions में given है, उनकी तो एक time की dependence है यहाँ पे. लेकिन यही चीज़ हमें importantly याद रखनी थी ना, कि ये velocity हम एक space के point के देख रहे हैं, ठीक? और हमें नहीं पता कि उसके थ्रू एट t is equals to 1 कौन सा पार्टिकल जा रहा है, t is equals to 2 उसके थ्रू कौन सा पार्टिकल जा रहा है, and so on. So whereas the acceleration, when we find it, or remember ये acceleration is of particles, this is dv by dt. It's the material derivative, right? It's the acceleration of particles, कोई भी फर्क, depending on what capital X or what we use. It turns out that their acceleration is actually 0. So this is quite interesting and important to note. और अब अगर आप इस पे थोड़ा और गौर करें कि why is it कि this expression as it is has a time dependence? It's clear, this has a time dependence. मतलब ये कि spatial description की velocity, so to speak, is changing with time. Why is that the case? That's because I had fixed myself on this position in space. So at t is equals to 1, मैं देखती हूँ तो उसके थ्रू कोई पार्टिकल जा रहा होता है जी a, और उसकी velocity होती है let's say 1. Whereas at some other time t is equals to 4, then there's a different particle. There's a particle b going through it at that time. Or b particle, it's a different particle. So it has some other velocity. Let's say 3 meters per second है या जो भी है. तो इस वजह से इस स्पेशल पोजीशन पे तो वेलोसिटी फील्ड जिसको अगर आप ऑब्जर्व कर रहे होते वो तो चेंज हो रही थी विद टाइम, क्योंकि आप बार बार किसी और पार्टिकल को देखते जा रहे थे. Whereas if you had just stuck onto A, let's say ये जो पहले जा रहा था, और सिर्फ इस ही की एक्सेलरेशन को हम देख रहे होते कि अच्छा A अभी यहाँ है, फिर A यहाँ है, फिर A यहाँ है, and so on. And if we had looked at its velocity, that is, we had looked at the velocity of in this description, और A को देख रहे होते, then that is, or when we were differentiating this directly, then we would have been looking at the acceleration of the particles, and that, it turns out, is actually 0 for this particular description, for this particular problem. So this is quite something to think about, right? Okay. Yep. Okay. What does it mean to be looking at the acceleration of a particle, and hence to be following a particle? Whereas what happens if you just stick yourself on to something in space and you're just observing a physical property at that point in space? Okay, right. This will become even more clear when we look at part B of this problem. And in part B, what we're doing is, yes, these are notes just discussing what I've just said out loud. That when I'm looking at just a spatial position, matlab yahi, again, when I'm just fixing myself on space, then I can see that the velocity is changing. That's because there are different particles passing through it at different times. Whereas if I'm just looking at the velocity of a particle, that will turn out to be constant, because I can see that the material derivative, that is the acceleration, is turning out to be 0. Okay, now let's see this problem in another way, which is when we find the path line. Oh sorry, इसमें तो solution ही आ गया directly. Let's try to do this, because this is also interesting. So when we find the path line, मतलब ये, I want to find how is the current position of a particle changing with respect to time. So x1, x2, x3 and time of y. How is this changing? So for this, I know the velocity, right? So for this, I need to think about again what the definition of velocity is. Now you guys may recall that my velocity is the partial derivative of xi with respect to del t, keeping capital X fixed. Right? So this implies that it's this, अगर मैं vi की expression ही लिख दूँ इसके आगे, which I know is kxi 1 plus kt. That's all I've done is कि वो vi लिख दिया इधर. Then if I want to find what x, small x, is in terms of capital X, basically I need to integrate this problem then. That's all that I'm doing essentially. Okay, so let's think about it. Please notice that there is a partial derivative of xi, right? It's like d of xi, whereas xi the right pair. So we do need to perform there's something called the separation of variables, right? Similar terms we have to bring to the left hand side. Variable सारे एक variable left hand side पे और एक variable right hand side पे हमें लेके आना पड़ेगा ताकि हम उसकी integration कर सकें. And what I mean by that is, if I want to keep my del xi here, then I need to bring my then I need to bring my xi variable on this hand side, ताकि मैं इसकी ये अब एक term है जो मैं integrate कर सकती हूँ. Right? This can be integrated with respect to xi. Whereas on the right hand side, then I need to take my time variable, ताकि then I have all of my k रह गया, sorry, k 1 plus kt. Then on the right hand side now I have all my time variables. Now this entire expression can be integrated. But what's important now is to note what the limits are, so to speak, for this integration. अब टाइम तो देखे ना 0 से जा रहा होगा at whatever time, क्योंकि reference time we always take to be t is equals to 0. Whereas what about the position? What is the reference, मतलब what are the limits going to be applied? Clearly I'm going to
Capital X.
Exactly, thank you, exactly right. Clearly I'm going to start from my capital Xi and then I'm going to end up at my unknown small xi. ऐसा ही है ना? तो अब इसकी इंटीग्रेशन करते हैं. So what does this become? This is xi being integrated with respect to xi. So that's just substitute the limits. And here this would be integration with respect to time. इसका क्या बनेगा? इसका भी वही बनेगा ना, k divided by k हो जाएगा. So this is k ln of 1 plus kt divided by k again. I think so. So this then gives me ln of xi. Okay, sorry, I was jumping some steps. I don't remember अगर आप लोगों की कितनी arithmetic क्या क्या चीज़ें आप लोग भूल चुके हैं अब. So ln of xi minus ln of capital Xi, which will be equal to k's cancel out. Just ln of 1 plus kt. अब इसका हमें ये logarithmic को remove करने के लिए I need to manipulate it. And I don't, वही मैं बात कही थी कि I don't know how much you guys recall, so let me just go here. When you have a logarithmic being subtracted by another logarithmic, then what happens is कि their terms, वो जो argument होता है, the minus is just this argument then divided by this argument. So this is actually just ln of is equals to, that is now the logarithmics क्योंकि दोनों साइडों पे similar हैं. So if we take the power e to the power, so these two both will disappear and all I end up with is that the small xi is actually equal to capital Xi 1 plus kt. Let me write it in bigger terms somewhere here. So small xi is equals to capital Xi 1 plus kt. Excellent. Now this is something which is very useful to us because I can confirm my result for A, which I found that my acceleration is just 0 by doing what? I remember that my velocity is del xi with respect to del t, right? Keeping capital X constant. So if I differentiate this with respect to time keeping capital X constant, what do I get? I get that my velocities are what? This A की t है अंदर. K times capital Xi. ऐसा ही है. Right? And I can see from here immediately okay, when I have my velocity in the what's the word material description, I can see कि oh ये तो time dependent है ही नहीं for a particle, such that if I find the acceleration, which is material derivative of velocity, there is no time derivative. So this is just 0. Sorry, there is no time dependence. So एक particle की एक capital Xi की velocity तो was fixed. It was a constant. And hence there was no acceleration of each of the particles. Okay. Does any of this make sense or you guys are just completely lost?
Ma'am, I have a question.
Ji, please.
Ma'am, does path line mean the path of motion of the particle in space?
Yes, yes, yes. The reason why it's just being called the path line is because this expression is telling me what the current position of a particle is, right? So what that means is that if I know the original position of a particle, then, or again the same old my frame of reference, then using this equation or this expression, I can find out कि वो particle, like particle A जो मैंने इधर draw किया, ये वाला particle, और t is equals to 1 कहाँ है, इधर हो गया, okay, t is equals to 2 कहाँ है, maybe इधर हो गया, t is equals to 3 कहाँ है, and so on. So it tells me the path that it's following. It's telling me the current position of that particle. Okay?
Okay, ma'am. Thank you.
No problem. Right. You guys may recall that you've already been assigned. I've given you an assignment. Let me see if I have it open somewhere here. Yes. So in the assignment, there are a couple of more problems just to get your concept of the velocity and acceleration completely clear. ठीक है जी कि what does it mean to be looking at the rates of changes of particles as compared to the rates of changes in positions in space. Okay, so yes, so just the discussion that we've had today will be helpful for you when you're doing the assignment. Perfect. Okay, so let's move further and just a few more minutes I'll take, inshallah. So let's once we've got the velocity and acceleration clear, then now abhi we hadn't really talked about deformations for now, right? So I want to get back into it, and the reason why we focused like a little while on the velocity and accelerations is because even those just by nature are important in fluid mechanics problems. Whereas now let's start to look at the rates of deformation basically. Okay, so previously you guys recall that when we were considering the solid mechanics aspect of it, we weren't per se interested in the rates, but we were just interested in their deformations, right? In their deformations happening in the sort of the vicinity of a particle. And we saw, okay, this is why we had started to come up with this definition of the deformation tensor, the deformation gradient tensor. Because it was telling us how is the vicinity of the particle in the current position, how has it changed with respect to its original. Okay, so this was the expression that we had looked at before. Sorry, can you see my screen again?
Yes, ma'am.
Okay, thank you. So now let's start to think about the rates of deformation, right? So essentially, if I want to think about the rates of deformation, all I need to do is, okay, let's just differentiate this entire expression with respect to time, essentially. So now let me find dx, rather than just dx, let me find dx ka dot. मतलब वो जो local vicinity have a particle, how is it changing with respect to time? Now this is of course going to be the material derivative, right? But हम particle, मैंने आपको कहा हम particle की बात कर रहे हैं हमेशा ज़्यादातर इन चीज़ों के अंदर. So again I'm interested in the rate of deformation around a particle. So hence why I've got the material derivative. Now I'm just going to do some arithmetic manipulation to see how these properties relate to each other. So right, so d of small dx है ये, right? dx dot निकाल रही थी. Then this dx I can substitute in terms of the deformation gradient tensor and the original reference vicinity of the particle. So it's just f dx. Now please notice that this is a product rule, but in this product, this dx with respect to time, it's the reference configuration. Reference configuration में there's no d by dx by dt. That's the reference configuration. वो तो है ही at a fixed time. So that's why this is so to speak a constant and it comes out. And then I just have the material derivative of the deformation gradient multiplied by dx. So I get f dot multiplied by dx. ठीक है जी. So dx dot comes out to be this expression right here. Let's see further though कि अब ये ठीक है f dot तो निकाल लिया, मतलब ये पता चल गया, लेकिन f dot itself, can it be related to some other quantities of interest, just as we had कि हमने f को in terms of it was I plus del u, right, displacement की terms में निकाला हुआ था deformation gradient को. Similarly, let's see what f dot turns out to be. Now, f dot of course is the material derivative of f, और f क्या था ये मैंने u वाले terms में लिखा था. Original जो था, we also remember it's del of xi with respect to del of capital Xj. So just popping that in there, substituting that in there, again changing the order of differentiation such that I get पहले I differentiate with respect to time and then I'll differentiate with respect to the reference configuration. So what do I get? This term right here. What is this? This is something I know. This is, of course, it's the material derivative. That's the rate of change of the current position. So material derivative है, so it's the rate of change of the. Sorry guys, my internet is acting up. So it's the rate of change of the current position of a particle, right? So that is just the velocity of a particle, right? So substituting that in, it seems to me now that f dot is the gradient of the velocity vector with respect to the reference configuration. लेकिन just अब ये है, this is, you guys are familiar with this del x क्या होता था, ये आपको याद है? हम जब भी हम differentiation with respect to reference configuration कर रहे थे तो हम उसको del naught से represent कर रहे होते थे. So this is, it's clear now that f dot is actually equal to del naught v. ये देखें, ये del naught है. लेकिन what ends up happening is that the more again क्योंकि fluids के अंदर rates of deformation use हो रहे होते हैं, then the convention in fluids is not to find derivatives with respect to the reference configuration, but instead I've changed my internet connection. Am I back? Sorry, अब आ रही है आवाज?
यस मैम आ रही है, लेकिन जो पिक्चर है थोड़ी डिस्टॉर्ट हो रही है.
Okay.
मैम डिसऑर्ड नहीं, एक जगह रुकी हुई है.
हाँ, वो तो मैं भी रुकी हुई हूँ.
होल्ड ऑन है स्क्रीन, होल्ड ऑन.
ओह ओके. क्या करें?
मैम 23 हो गए, बस फिर यहाँ तक ही रखते हैं.
नहीं नहीं नहीं, thank you. Okay, please, now is it back?
Not for me.
No, ma'am.
No,
मैम सिर्फ
ma'am.
गिल रिव्यू शो हो रहा है मैम, एकदम सिर्फ एक
No.
Okay, thank you. Let me still. What about now?
नॉट येट मैम अभी
मैम
आ
आप आ रही.
Okay, perfect. Okay, perfect. Thank you. So let's get back into it. So I was saying for fluid mechanics, the convention is not to find del naught. मतलब ये कि not to find derivatives with respect to the reference configuration particularly, but instead to find derivatives with respect to the current configuration. That is to find ये del naught के बजाय to find these. एक सेकेंड, कहाँ जाऊँ मैं, एक सेकेंड. del naught आप लोगों को याद है ना कि this was del by del capital X. So all I'm saying is कि even though हमने f dot को we found out just from this expression right here that it's del naught v, लेकिन the convention in fluid mechanics is to use del by del x. ओके इसी वजह से हम इस एक्सप्रेशन को चेन रूल यूज़ करके कन्वर्ट कर देते हैं फ्रॉम derivative with respect to capital X into derivative with respect to small x. And how we do that is just by कि आप चेन रूल अप्लाई कर दें, तो del vi with respect to del small x कर दें and then multiply by the derivative of small x with respect to capital X. Okay, ताकि अब इस चीज़ को हम we can write this as del x, ये this is अब बहुत ज़्यादा चीज़ें लिख ली हैं. This is the derivative of velocity with respect to the current position. So it's del small x v multiplied by this expression, which is of course ये तो हमारा पुराना deformation tensor है, deformation gradient tensor है. So this is del x v and this is f. So hence our the material derivative of f dot, that is when we're interested in the rates of deformation, we find this expression right here, that the rate of change of the deformation gradient is this one right here. Okay, now again this is important whenever we're interested in any question.
Yes, ma'am.
जी please.
मैम जो मटेरियल डेरिवेटिव ऑफ एफ है, इस केस में जो थर्ड नंबर पे जो आ रही है यानी ड्यूरिंग डेरिवेशन, वो किस तरह अचीव हुई है फ्रॉम सेकंड थर्ड?
From here to here?
नो मैम, मटेरियल डेरिवेटिव ऑफ एफ,
This one.
सेकंड हमने सॉल्यूशन निकाली, थर्ड जो है उसमें किस
यहाँ से यहाँ? Have I lost you guys? Hello, is it me or is it the person who was asking? दानिश पूछ रहे थे और उन्होंने nothing. Can someone hear me, please?
Ma'am,
I'm sorry, maybe there's something wrong with my internet. Could you repeat your question, please? It's from going from here to here.
Yes.
Okay, so going from here to here, I've just swapped the order of differentiation. right? Pehle when I've written it down like this, then I am performing the derivative with respect to time first, and then this one, right? So there's nothing stopping me कि मैं पहले with respect to time कर लूँ और del xj को बाहर ले जाऊँ. Order of differentiation हम change कर सकते होते हैं, right? Because it's what's the word? Distributive, commutative, या जो भी कहना है.
Okay, ma'am. Thank you.
So that's what I've done. So I've taken the time derivative first, and then I'll take I'll find the gradient after that. ठीक है जी. So only this is the manipulation that's happening from here to here. Right, okay, so the rate of deformation gradient is something that we have just found. And again, I've said that there are so many different quantities that we keep introducing in continuum. And the reason is primarily because in various fields these things are used and they pop up. So just for this purpose, in the assignment number 2 that I've given you guys, there's also there's a question. The question number 1 is related to a particular field which is crystal plasticity modeling. कहाँ पे है वो? मेरे ख्याल में मैंने नीचे, I hope के, yep, where I've attached a chapter from a sort of crystal plasticity की book से related था. And if you take a look at that, again वही बात है ना, if you were working in this field, then you would see how each of these things come into play. So for example, this is something that we've already talked about, deformation gradient. Also what will pop up here, I think deformation gradient ka rate bhi pops up. Look at this, f dot. And that's exactly what I'm discussing right now. And my point is that these various different physical properties, depending on which field you're in, they have some significance there, and you need to be familiar with them. So this is the rate of the deformation gradient, and it is used in time-dependent solid mechanics. It's also used in compressible fluids and their mechanics. So again, this is a slightly important physical property which may chase after you depending on which field you go into. Right, okay, so इसी चीज़ से ना अब हमें let's start to move to define some other important things. So first of all, as you've seen that we've come to some of these results we derived here, right? So this is the one previously when we were considering the deformation gradient. This is the one that we've just derived in the previous slide. Okay, how is the rate of the change in the vicinity? And then finally we've just seen के rate of the deformation gradient क्या होता है. That's this expression right here. इसके अंदर there is this del xv which is popping up. और you guys notice कि ये del xv जब हमने acceleration भी लिखी थी, right? Acceleration in when it was known, when the velocity was known in the spatial coordinates, then we had del v by del t. Excuse my missing the i's and stuff. Plus v j del vi with respect to del xj. Now this del vi with respect to del xj is exactly this thing. It's del x of v. और ये जो चीज़ है ना, जिस तरह displacement gradient हमने पहले देखा था, उसी तरह ये velocity gradient is also something pretty important. और इसी के terms में let me manipulate this thing further. So I've got my f dot, or f dot turns out to be this. So if I substitute f dot in here, put this in here, then I'm getting कि f dot तो है del x v f. So dx dot क्या हो गया? Del x v f times dx. F dx is dx, small dx. Whew. So small dx turns out to be this. Now is the important thing. कि जिस तरह हमारे static case में we had been talking about the deformation gradient f, right, which was giving us some measure of deformations. उसी तरह जब हम rates of deformation की बात करते हैं, then f dot के बजाय instead this velocity gradient is the one that gets used very frequently. So this del x v velocity gradient gives us some measure of the rates of deformation in a particular problem. Okay, and what is this deformation, this velocity gradient? It's the differentiation, as we've discussed, with respect to small x. Hence why when I write down the entire tensor, velocity gradient tensor, it is this, right? इससे भी देख लेना tensor notation में, it is vi with respect to j, vi comma j. ठीक है, where the differentiation is happening with respect to small x. So these are all the 9 terms of the velocity gradient. ठीक है, and this is a pretty important thing. Abhi, let's see further why it's actually a pretty important thing. Okay, just as before, there were some properties which popped up, or we saw ke मेरी तो कॉल ही ड्रॉप हो गई है. Guys, I'm back. Sorry I keep dropping. We can't stop because it's literally 5 minutes left. उस्मान, तो आपको किसने कहा था जॉब के साथ मास्टर्स करें? हाँ, मुझे ये बताएं आप. मास्टर्स का तो कसूर नहीं है ना, वो तो नहीं आसान हो जाएगा. Just literally 5 more minutes, okay? Okay, so coming back, I was just the point was कि we've come to this velocity gradient. मैं थोड़ा सा तेज़ कर लेती हूँ अगर आप लोगों की कैपेसिटी वो थोड़ी लो होगी है. सो जस्ट एज बिफोर हम लोगों ने डिस्प्लेसमेंट ग्रेडियंट को सिमेट्रिक और स्क्यू सिमेट्रिक पार्ट्स में डिकम्पोज किया था, उसी तरह हम इस वेलोसिटी ग्रेडियंट को भी कर सकते हैं. ओके, सो दिस del x v which I've written down right here, please, this is very important, so just give me 5 minutes and keep pay a little bit of attention. Okay. So I can decompose this. It's a symmetric matrix. I can decompose it into, sorry, it's a square matrix. I can decompose it into my symmetric and skew symmetric parts, जिस तरह हमने पहले किया था. और let me represent the symmetric and skew symmetric parts by these 2 letters. Then my symmetric part, as before, is जिस तरह जो उसकी expression है जो symmetric part की होती है. Okay, so I've just written it down right here. This is known, this is being represented by D. And the skew symmetric part is going to be this one. उसमें वो the tensor में से उसका transpose subtract किया जाता है. Right, so it's this expression right here. ठीक है, ये हम पहले भी कर चुके हैं, इसलिए you guys are familiar with this. Now comes the interesting part, which is that these 2 things, this D and W, are actually further interesting physical properties. This D is actually known as the rate of deformation tensor, or in other words is also known as the strain rate tensor. और होता क्या है कि इस D में मतलब ये कि velocity gradient के, this is the velocity gradient, velocity gradient का जो symmetric part है, this rate of deformation tensor, that actually tells us the rate of straining of the material, yeah, the rate of straining of a particle. And as before, as was the case of the strain tensors, इस case में जो diagonal parts हैं, these ones, these tell us the rate of normal strains, मतलब ये the rate of extension या फिर compression of a particle, whereas the off diagonal terms, they tell us the rate of shearing. Okay, so this is extremely important then, because इस D के अंदर velocity gradient के symmetric part के अंदर rates of strains हैं. Now just one tricky part, कि unfortunately this D is not actually directly related to epsilon का dot. ठीक है, ये directly infinitesimal strain rate का infinitesimal strain tensor का rate नहीं है. Instead it's slightly indirectly related to it, and I won't discuss it right now, because when you do encounter it and you get to a particular problem, then you can look up, okay, how do we get from this rate of deformation tensor to directly finding, let's say, the rate of green strain tensor या फिर the rate of the infinitesimal strain tensor. Okay, इसी वजह से इसका नाम ना directly ये नहीं कहा जाता कि it's the rate of the infinitesimal या क्या. It is indirectly related to it, or it gives us a measure in any case. मतलब ये कि rates of straining इसके अंदर हैं incorporated. Okay, but it's not directly equal to these two things. Right. Secondly, now let's come to the skew symmetric part. Now the skew symmetric part of the velocity gradient is known as the spin tensor, and it's represented by W. And as was the case for जब हमने displacement gradient को del not U को decompose किया था in terms of the infinitesimal strain gradient plus something जो मैंने कहा था मैं छोटे W से represent कर रही हूँ, the infinitesimal rotation tensor, उसी तरह अब ये del x V जो है that's being decomposed into D and W. And as before, this was related to straining और जो चीज़ें stresses cause करें, whereas this was related to rigid body motion. And the same is happening with the velocity gradient, that this W is actually the spin tensor. This basically describes how the vicinity of the particle is rotating, or how it's spinning, in other words, या फिर what is the rigid body rotation in it. No contribution of strains in this W. Okay, or what are the terms? It's a skew symmetric component of the velocity gradient. So if I just write those terms down, they are these. और इसमें अगर आप और गौर से देखें तो ये जो skew symmetric part है ना, मतलब आप एक तो definition से ही पता है skew symmetric होता क्या है, which is equal to its minus of the transpose, right? So if you take a look here, then there are only 3 independent terms in this one. मुझे पहले भी बोलना चाहिए था, sorry. D के अंदर कहाँ गया? D के अंदर there are 6 independent terms. It is symmetric, so these are the only independent terms in this. ये तो symmetric part है ना, so 6 symmetric terms. Whereas for the skew symmetric part, there are only 3 symmetric terms, 3 independent terms, such that अगर मैं इनको कुछ call कर लूँ, let me call this one W1, this one W2, and this one W3, then I can actually write my spin tensor as a vector, and this is pretty common, which is के fluid mechanics में spin tensor की जगह spin vector या फिर something else known as the vorticity is used to describe the rigid body rotation of a fluid flow basically, right? और ये vorticity जो है, it just contains these three independent terms of the spin tensor. और spin tensor क्या है? It's the anti-symmetric or skew-symmetric part of the velocity gradient, right? Okay, so I know I was being very annoying by not stopping, but as you can see, it was just ये कुछ चीज़ें हम और physical properties that we have encountered before. We just I wanted to finish this part and see where is all of this again coming from. As you've noticed again with continuum, we're not talking about directly कि physically हम वो चीज़ें observe करते हैं नहीं, we're just seeing how this is all popping up from looking at a first principle analysis of the kinematics or just of the motion of a continuum. और उससे we are getting all these interesting things जो हम physically भी use कर रहे होते हैं, right? So that's it for today. Please, I've suggested some problems for you guys to do. You don't need to submit them. It's up to you if you do it or not. I, in particular, would like to recommend that you look at Reddy's problem 3.5. ठीक है? अगर time मिले आप लोगों को, वरना you have to do the assignment and submit it for next time. So that's it for today. I'm available for any questions which might be outstanding, but otherwise you're free to go. Thank you all. Where is my team?